Let's get to it. So reaction rates and stoichiometry. So we previously just finished up looking at what happens when you have a 1-to-1 ratio. Basically, we know that when we gain one, or I'm sorry, when we lose one, that's why the negative is there, we lose the other. It's a 1-to-1 ratio, pretty simple, pretty straightforward. Things get a little bit more complex when we're dealing with a basically not a 1-to-1 ratio. So let's take a look at the reaction of H2 plus O2 yields H2O. So we're going to balance this out. We end up with 2H2 plus O2 yields 2H2O. Fair enough. So in this case, we have to think in terms of, again, when I write this out, rate is equal to, again, what we're going to look at is the change in concentration of H2 over time, which is equal to, and we'll talk about those equal signs in a bit, O2 all over time. And finally, constant change delta concentration of H2O over time. Again, all present. These are equal signs, meaning these rates will be equal to one another. Okay, the fact that these are all equal to one another is kind of the important sign. So we're going to take a look at the oxygen one first. So rate is equal to change in oxygen over the change in time. Are we missing anything? Well, because we're losing oxygen, this has to be a negative sign out front. We always have negative signs for any of the reactants because we're losing those. Okay. Now let's think about O2 versus H2. So for every one oxygen that I lose twice as much. I lose 2 H2. So if we set the equation like this, essentially what I'm saying is, again, let me just toss in a negative here because the negative is going to be there. I put it out front for a reason. You'll see in a second. So in this case, these are not equal to one another because right now I'm losing hydrogen twice as fast as I'm losing the oxygen because 2H2 yields 1O2. So we're going to do a little bit of a shift here. Again, because they all have equal signs, right? These two, in order to be set equal to one another, we have to account for the fact that I'm losing twice as much hydrogen as I am oxygen. So if I'm losing hydrogen twice as fast as oxygen, we're going to put the 1/2 in front. So 1 over the coefficient, just like oxygen is 1 over the coefficient of 1. Okay, so minus 1/2 H2 is equal to minus the loss of my oxygen because, again, hydrogen is going away twice as fast. Therefore, we need to balance it out in order for them both to be equal to the rate. What do we expect to go in front of H2O? First of all, it's going to be plus because it is a product. I'm gaining it. So 1/2 because there's a 2 out front. So for every oxygen that I lose, I'm gaining 2 waters. So it means I'm gaining water twice as fast as I'm losing oxygen. Therefore, so that's what we have. This is what we call the rate expression. And we're going to look at this in a different way. I'll use a smaller pen here. We're going to look at this in a different way. So rate expression. This right here is known, this whole thing, I should say, is the rate expression. So yeah, this whole thing is the rate expression, all of that together. So we can generalize this. So we have A is equal to A plus A, B coefficient times B yields CC plus D. This is kind of the standard equation that we use. So the rate is equivalent to, I am losing some concentration of A all over the change in time. So delta A over time is equal to 1 over B change in concentration of B over time. So again, the 1 over the coefficient, the negative sign because I'm losing A, and same thing for B. We take a look at C, 1 over coefficient, change in concentration of capital C over change in time is equal to plus 1 over D, change in concentration of D over time. So again, same exact thing. Again, this is the rate expression. Okay, so one more time. A corresponds to that coefficient. Concentration and the fact that it's a reactant shows you that the fact that it's a reactant is just going to be, that's why it's negative. Good. So how much, write out the rate expression for this reaction right here. And so we'll cover this in class. So when we are looking at concentration and rates, because concentrations are involved in the rate laws, we have to think about these. So first of all, changing the initial concentration is going to give us a set of rates. So here we have this overall reaction that we're running. NH4 plus NO2 yields N2 and 2H2O. So we start with different concentrations of NH4 and NO2, and we look at the initial observed rate to see what actually happens in these cases. So what we notice here is this is the same. So there is no change. There's no delta there. So whatever change in rate is observed, it's all due to the change in concentration of NH4 plus. So if we look at the NH4 plus, we have doubled the concentration. Notice the rate has also doubled. So in this case, by doubling the concentration, I double the rate. So this gives us information about NH4. And the most important thing about this is this information has to be done through experimental means. All kinetics is determined by experiment. What this means is this equation gives me zero information about the kinetics. I can't look at that equation and say, oh, doubling the concentration of NH4 doubles the rate at which it runs. The only thing that allows me to determine the pace at which the reaction goes, the rate, is experimentation. So actually doing experiments like we did in class, that's what is going to determine that. Well, we looked at NH4, so let's keep NH4 constant. And same, right? ME, there we go. What happens to NO2 minus? Again, we've doubled the concentration and the rate has also doubled. So the same effect. So if NH4 doubles, if NH4 doubles, as we saw up here, rate doubles. If NO2 minus doubles, rate doubles. So what does that mean if I double both of them? If we double both of them, what we would expect to see is the hopefully the rate would quadruple. Okay, so we do see those changes. They are, and now that leads us to, so what we know about this equation is that rate is directly proportional to NH4 plus. That's the first set of data, or the first two reactions looked at told us. And we also know that the rate is also proportional to NO2 minus. So they're proportional in that event. Therefore, what we can actually say is, well, rate is proportional to the change in NH4 plus times the rate of NO2 minus. So they're proportional to one another. So they're all proportional to the rate. We don't really do anything with this in actuality, right? There's nothing that I can do with this proportionality. It shows me the relationship between rate and the two concentrations, but this is problematic. We're used to seeing that as kind of an equal sign, right? So my question to you is, how do we change that into an equal sign? There's a mathematical way that we actually turn this into an equation. And hopefully you remember this from math. So if I want to turn that into an equal sign, what do I need in order to do that? And this goes for whenever you want a relationship and you want to get rid of the proportionality, what you do is you just simply add a constant. So the constant K is going to basically set these things equal to one another. This K right here, first of all, it must be lowercase because we're going to use a capital K in the next chapter. So this has to be lowercase. So lowercase k is a rate constant. Okay. This whole thing together is what is known as a rate law. It is the thing that determines the rate at which this reaction goes based on experimental information. So what exactly is a rate law? Okay, so a rate law is the relationship between reaction rate and concentration of reactants. Okay, so and as we're seeing, rate and concentration of reactants. So it's going to show that relationship. Again, the most important thing that I can't emphasize enough, it is experimentally determined and must be experimentally determined. Must be experimentally determined. So we can't determine a rate law without an experiment. That's it, bar none. So when we look at the general reaction here that I was looking at, I have zero information about the rate law. I can write a generalized rate law. The general rate law for this equation is rate is equal to rate constant K, lowercase k. It's a terrible K. Let's try again. Rate constant K times the concentration of A raised to some value, and we're going to talk about those in a bit, times the concentration of B raised to some value. So a couple of things about this. These here, I'm not going to bury the lead. These are called the reaction orders. And the K is going to be our rate constant. All of these have got to be determined experimentally. Experimentally determined. Okay. Another thing that we're going to notice is I have A and B. Notice that C and D are nowhere to be found. In fact, I can just cross those out because I don't really care about them. The only thing in a rate expression is going to be reactants. The only types of products, reactants are the only thing. Reactants only. In rate law, I should say, not an expression. So reactants only in a rate law. Good. Okay. So we should be able to draw the, we'd have to do an experiment like this in order to calculate the values of X, Y, K, X, and Y. And we're going to do this in class. It's a really, yeah, it's an easy way to do it. In fact, I'll do one before I set you guys loose on it. So let's talk about the idea of reaction order. So I'm going to talk about these first. So first of all, the reaction order is with respect to each reactant. So this superscript is going to tell you with respect to each reactant. So this one right here, we would say that this is first order with respect to the concentration of A or substance A. Okay, this one right here would be second order with respect to B. Here, I'm going to say that this is second order with respect to C, and first order with respect to D. Okay, these are all different equations, different reactions. But what we can say about the overall is we can also say that reaction order overall can just be simply found by can be found by adding exponents in the reactants in the rate law. So in this case, if I add these two together, I've got third order overall. So third order overall. Why that's important is because if I, well, in fact, we're going to look at this, but if I change just, in this case, if I change just C, it's going to affect it this way. If I change just D, it's going to affect it in this way. But if I change those both together, it's going to be a third overall change, okay? So we don't really need to understand those quite yet. In fact, let's take a look at what these things actually mean kind of when we put them together. So let's just take a closer look at these exponents. Again, those exponents are reaction orders. I know it doesn't make much sense now. It does when we start looking at data. So in order to kind of understand this, let's just plug in some numbers. So let's take a look at a first order reaction. If I have a first order reaction, that means that we can draw out a rate law. K is equal to concentration of A raised to the first, right? That's a first order reaction. What about a second order reaction? What would you have? Rate is equal to K concentration raised to the second, okay? So that is a second order reaction. Let's just assume for all of these examples, let's assume that the concentration of A is equal to 1 and rate is equal to some value 1. And by the way, we're going to ignore K for now. It will come into effect later, but yeah. So if we assume that, that means that the rate is equal to 1 K times concentration 1 raised to the first, and that's it. So my question ultimately is, well, what effect will doubling the concentration of A have? What is this order going to do when I double the concentration? Well, let's take a look. So what is the new rate when I take the concentration and I double it? So here's my concentration and I've doubled it, raised to the first. Well, 2, again, we're ignoring K. 2 raised to the first is just simply 2. What that means is rate has doubled. Right? So 2x concentration equals 2x rate. Just like in the first example we did, by doubling a concentration, it doubles rate. So that's what first order does to a reaction. What happens to the next one? So again, let's assume A is equal to 1 and rate is equal to 1, and I square it. Well, what happens when to rate, when I double the concentration, rate actually comes out to 4 times greater. So rate quadruples or goes up 4x. So again, 2 times the concentration equals a 4x to the rate. That makes sense? So again, if you forget like, oh, does it double or whatever, you can just plug in numbers and you can get your answer. Now, this is a special case, but we do in fact have this quite often. Zero order. Zero order is a thing as well. So what happens for zero order? Well, what does zero order look like? Rate is equal to K concentration of A raised to 0. Again, what happens when if rate is equal to 1, concentration of 1 raised to the 0, what happens when you raise something 1 raised to the 0 simply goes out to 1. What happens when I double the concentration? K, 2 times concentration raised to the 0. We should have 0 as our new, 1 is our new rate. So we go from here to here. What happened to the rate? No change, right? So there is no change in rate. What that ultimately means that there is no effect. So changing the concentration, I don't think I have to do anything else. There's no changing concentration when it's zero order has no effect on the rate. Does that make sense? I hope so. We're going to get more into determining reaction orders, but the order with respect to something is going to show you how it changes, right? So for this one, for example, I know that if I double C, I know the rate is going to double. If I double D, I'm sorry, quadruple, I should say quadruple. And if I double D, I know that the rate is going to double, right? So that's the information that we pull away from this. Okay, so this is all leading to some experimental stuff. So I would like you to write out the determine the reaction order for the component for each component in the overall reaction. Okay, so these are the experimentally determined rate laws. Okay, so if these are the experimentally determined rate laws, it is blank order with respect to HI, blank order with respect to N2O5, blank order with respect to NO, so on and so forth. In fact, yeah, that's what we're gonna look at. Okay. I'm gonna actually add one more here. Let's say, I don't know. Yeah, I'm gonna add one more. 2H2 plus O2 yields 2H2O. And my rate law for this is just simply K concentration of O2 squared. So also do that one as well. So let's talk about rate constant units, K. Again, you don't need to memorize this. And in fact, it's going to kind of fall out. So we're going to do this in a little bit of a different way. We're just going to look at, again, let's write out any first order, second order, and third order reaction. So rate is equal to K times concentration of A raised to the first. And we'll do the same thing for these two. Rate is equal to, in fact, you should probably pause this. I'm just going to do the skeleton of them. K concentration of A. Yeah. Raised to the second, B raised to the first, because overall that would be third order. You could certainly say rate is equal to K concentration of A cubed. That's fine too. So any of those, but that's the idea. So let's talk about units. Rate is always going to be in molarity per second. We're looking for what K is. Yeah, so molarity per second. And we know that the concentration has got to be in molarity. So what we end up with is rate in molarity per second is equal to K times molarity raised to the first. How do we solve this? Well, we are going to divide both sides by molarity. Molarity cancels, and the net result is K equals 1 over seconds. That's the final unit. Or we could also say seconds to the -1. That is also correct. Okay, good. So that's pretty much it. So let's try the next two. What is the, actually, you guys can do these. You can pause it here, determine what the second order and third order value of K is, and play it again. But here we go. So again, rate, and I'm just going to skip ahead. So rate is in molarity per second is equal to K times molarity squared. Divide both sides by molarity squared. Right? Molarity, one of the molarities cancels out, both of those do. And what you end up with is K is equal to 1 over molarity times seconds, or molarity to the -1s, seconds to the -1. Again, we're doing these just by understanding how units work and what we're required to have for both concentration as well as rate. And the last one, rate molarity per second is equal to K times molarity squared times molarity, which together comes out to be molarity cubed, all divided by molarity cubed in order to move it to the other side. Molarity cancels all but two of those. What you end up with is 1 over molarity of K equals 1 over molarity squared times seconds, or molarity to the -2 times seconds to the -1. So again, either of those two works. And that's it. Interesting one. In fact, I already tell you, but what happens if it's 0 order? So again, special case, rate is equal to K times concentration of A raised to the 0. Again, molarity per second is equal to K times molarity raised to the 0. This just simply goes to 1. So K is equal to molarity per second. Doesn't make much sense in terms of K because it's strange that it can keep changing, but that's in fact what it does. Good. All right. So what does the magnitude of the rate constant actually mean? So what information can we actually get out of this? So K allows for the evaluation of reaction rate. The general rule for this is if K is greater than or equal to 10 to the 9th, it is very fast. It's almost instantaneous. Okay. If K is less than or equal to 10, it is slow. This means like on the second time scale, the clock reaction that we do for the lab is going to be around 100. So it happens in minutes or seconds, those types of things. So slow reactions, as you start to get low below 10, one takes maybe hours or days. So we start to get longer and longer. All right. So yeah, so we are going to take a look at a bunch of experimental data, and our goal is to be able to find, in this case, I use M and N before I use X and Y. So X and Y, we're going to take a look at this. So let's not worry about this. We're just going to jump into an example. So what we're trying to do here is we have a generic equation. We want to solve a couple of things. We want to determine the rate law. We want to determine the rate constant and reaction rate under these special conditions, okay? I just want to make sure that they're not there because I think one of these I messed up on, but here we go. So this is the experimental data. So we ran experimental data, we looked at initial first rates, and this is what we've got. So this is how we do a calculation like this. So first and foremost, the first thing that we do, rate is equal to, again, this is my equation. So write out the generic rate law for this. So rate is equal to the concentration of, almost there. Rate is equal to K times the concentration of A raised to the X, concentration of B raised to the Y. That's our generic rate law. Again, I do not know K, X, or Y. It's going to come out of this information. So we are going to solve for K, X, and Y right now. We're going to solve for X and Y first, then we're going to solve for K, and then we're going to have our overall actual rate law. So this is our goal, is to turn this to fill out what K, X, and Y are. So our goal is to figure out K, X, and Y. Okay, good. And we can, as soon as we know what it is, we can substitute that in. And the way that we're going to do this, by the way, you can certainly look at this and determine them. You get good, so you can say, oh, I know exactly what that is just by looking at the rates. But we're going to look at the foolproof way to do it, just in case the numbers are a little wonky. So in order to do this, this is how it's going to go. So what we're going to do is I'm going to look at, let's take a look at experiment 1 with experiment 2. So experiment 1 and 2, what we notice is whatever change we observe here is all going to occur because of what's going on with B, right? Because B changes, A does not. So let's evaluate experiment 2, experiment 1, and experiment 2, because only concentration of B changes. If you're given more than 2, you always want to make sure that you're choosing one that you have one variable at a time. You're not allowed to evaluate 2 variables at a time because this method won't work. So we're always going to take the bigger numbers. So concentration of 2 is a little bit bigger. So I'm going to put experiment 2 over experiment 1. And what I'm simply going to do is I'm going to plug in all of the values. So I'm just going to take all of these values. So I'm going to take, for experiment 2, I'm going to take the rate and I'm going to plug it in here. I'm going to take the concentration of B, I'm going to plug it in here. And I'm going to take the concentration of A and I'm going to plug it in. So essentially I'm going to plug in for A, B, and rate the experimental values that I have. So this is what it looks like. So we have, for experiment 2, I have 4 times 10 to the minus 5 is equal to K, because we don't know what K is yet. Concentration of A being 0.100 raised to the X times 0.200 raised to the Y. There we go. And then I'm going to simply divide this all by the values for 1. 4 divided by, or 4 point, yeah, so 4, again, all of these are for experiment 1. These are for experiment 2. So let's substitute these in. K doesn't change. 0.100 raised to the X and 0.100 raised to the Y. Again, I'm just going to point out the fact that all of these values get plugged in here, right? So all of those correspond to this. All of these correspond to these, okay? All right, so let's take a closer look at this because we can simplify this a little bit. We're in a situation here where this simplifies down that doesn't change, that equals 1, right? Equals K over K, that turns into 1 as well. Yeah, this right here, we have 0.100 raised to the X over 0.100 raised to the X. That right there simply also turns into 1, right? And what are we left with? We're left with 0.200, 0.100 raised to the Y. Another way of saying that is that's just simply 2 raised to the Y, right? So if I combine all of those terms, 1 equals 2y, y equals what? That's right, y equals 0. So it is 0 order with respect to A. So we can plug in right now, I can in fact change this. This is what equals y. I can plug with respect to B rather. So I can plug that in right now, right? So we could just plug in that 0 for y because we now know it. But let's keep moving. Let's figure out what A is. So again, I want to figure out how to determine, this time I want A to change and I want B to remain constant, right? So does that work? It does not, right? I want A to change, B to remain constant. So I'm going to use this one as well as this one, and we're going to plug those in. So again, same exact concept. It's a different color, so it's a little bit more obvious. So we're going to use reaction 3 with reaction 1 to do this calculation. So this time I'm going to put 3 over 1, and we're going to run through the same exact setup. So reaction 3, 16.0 times 10 to the minus 5 is equal to K, concentration of A, which is 0.200 raised to the X, 0.100 raised to the Y, and for reaction 1, 1 times 10 to the minus 5, K over 0.100 raised to the X, 0.100 raised to the Y. So again, we're going to go through the same thing. 16 divided by 4 is going to give us 4 equals k over k gives us 1 times 0.2 x, 0.2 raised to the x over 0.1 raised to the x is simply 2 raised to the x. And then this is equal to 1. So overall, what I have is 4 is equal to 2 raised to the x. Solve for x. And what do you end up with? X is equal to 2. So there we go. So now I can rewrite the rate law. So my rate law, rate is equal to k times concentration of A raised to the x, which we determined to be 2, B raised to the 0. Do I need that B there? Because it will always be the same. I do not. I can simply just say, yeah, that is my new and final rate law. Great. So that was step 1. That is solving for the rate law. So now we're going to take a look at B. In order to solve for K, K is a constant. So if K is constant, we simply just say, all right, well, let's just plug anything that we want. Solving for K is just simply saying, all right, well, my rate law is rate is equal to K concentration of A squared. I'm just simply going to say, well, let's just plug anything in. So I'm going to plug in reaction 3, 10 to the minus 5 molarity per second is equal to K times concentration 0.200 molar squared. And solving for K, so just do the math here. K is equal to 4 times 10 to the negative 3. 1 over molarity seconds. And there we go. There's my K value. It's a very slow reaction. That's the other thing that we know. Yeah, so that's it. Now that we have K, we can do the last step. The last step, C, is to solve for rate when concentration of A is equal to what? Concentration of A is 0.050. And concentration of B is equal to, what was it? 0.100 molar. And all I simply have to do is plug in rate is equal to my K value, which is 4 times 10 to the negative 3, 1 over molarity seconds, times A 0.050 molar squared. And I don't care about what B is because it's not in the rate expression. And there you go. Right. So that's how you do those calculations. Yeah, that's it. That's how we do it. So now the question is, can you do it again? And yeah, and I'll come up with some more examples that we can go over because this is an important thing to know how to do. Yeah, that's it for rate laws. So hopefully you got it.